should I record it? Okay, I will start recording right now. I'm going to change to my pad so I can record something. I'm not going to use the full lecture hour because I'm going to record the problem solving on another video and I will send out a link. So I will basically give you some idea about the Laplace transform based on the slide, and the problem solving I will leave it to another video I will send you. I'm sorry, I forgot to turn on my mic. So can you guys hear me now?
Yeah.
Thank you very much. Sorry about that. And I'm recording, so that's good. Okay. All right. Again, as I was saying, your coming exam is not going to cover the inverse Laplace transform, but we will give you an idea what an inverse Laplace transform is. It's going to be mainly on the Laplace transform. And we're going to tell you why do we do a Laplace transform, what is the benefit of doing a Laplace transform, and what is the Laplace transform, and also the inverse Laplace transform. And we're going to briefly look at the properties of Laplace transform. As I mentioned to you, this two table that you can find from the chapter 12.4 and 0.5, there's a functional Laplace transform, operational Laplace transform. There is a table 12.1, table 12.2. One is for the Laplace transform, the other one is for the inverse Laplace transform. You might want to have those table handy when you take in the exam. You don't have time to go through those things. Just make a copy of that table or have that table ready when you're taking the exam. It's going to help you on the exam. And I wanted to also mention about these three important functions. We kind of covered that before. But this is mainly used in the Laplace transform. It's going to be closely linked to the ramp function, the step function, and also the impulse function. Then how to get the Laplace transform, inverse Laplace transform, I will do another video tape, and we are not going to cover it here, so I will do another video to talk about that. Okay, so let's first look at what is Laplace transform and why we do a Laplace transform. So when we deal with the AC circuit, we're looking at the source of the power, which is the voltage or current. They're like a sinusoidal. And if you remember when we start with the chapter 9, we say, well, it's a sinusoidal. So if we look at the response of the circuit, we only care about the steady state response. And there actually something is not just steady state. If you think about the equation of those second order differential equation with a sinusoidal input, and that could be something like this. This is actually a general thing if you have an AC circuit. When you have an AC circuit, you supply with a voltage, which is sinusoidal function with omega t and phase angle, and then your circuit is going to characterize the circuit into a 2 alpha plus an omega 0. The frequencies, the Napier frequency and resonant frequency. And we kind of skip the process if you actually solve this in differential equation. The standard process of solving this is you make the equation, the left-hand side equal to 0, you find the natural response. You use the V and cosine omega t plus theta, you find a particular response. You add them together, you get the total response. Then you use the initial condition, right? So the process, if you wanted to solve it in what we call the time domain, you do homogeneous solution, and then you find particular solution. How do you find a particular solution for the Vn cosine omega t plus an angle? You assume the solution is a combination of a sine and cosine with a coefficient, maybe K1 and K2. And you put that back into the equation. This process at least spend you half hour easily to find a solution. So, and then the process is that you have to find a complete solution. You actually have to find what is the coefficient for those solutions, right? That is the difficult part that you, as I said, if you actually go back to what you learned from the you actually going to find the derivative of the solution, and then you apply two initial conditions, then you find the coefficients. So this process is taking too long. And all this transformation is just trying to simplify the problem into another domain. So Laplace transform is similar to the phasor domain, but the phasor domain only do the steady state response. It doesn't give you the complete solution. It give you the steady state response, which means when time goes to infinity, what does the solution looks like? But the solution is not like that. The solution is not only including the steady state response. If you're interested about the very beginning of the response, which is not going to be steady state response, and that part of the response is what we call the transient response. The transient response is the response at the beginning of the circuit and what will be the current or voltage do before they actually reach to the steady state. The normally steady response is the particular solution. So particular solution actually give you the steady state response. So if you wanted to get a transient response, then you have to actually go through this process. So phasor only works for the sinusoidal function. It only gives you so we need a new way. We need a new way where the new way is this one here. This one is called the Laplace transform. Laplace transform gives us another domain. So this domain is also called a frequency domain. And or another way you can say this is an S domain. So this one is going to give us an S domain. So if you do a Laplace transform, after you do a Laplace transform, normally if this is a function of f, then we will write this function with a capital F and as a function of s. It's not a function of time because once you transform that into another domain, it's going to be in another function. You're going to see a lot of transformation in the future. One of the most famous transformation is called the Fourier transform. The Fourier transform is very similar to Laplace transform. They use different function to do the transformation. When you do a transformation, it means you represent the same thing in different space, like rectangular coordinate. You can transform that into a polar coordinate. They represent the same thing, but they use different way to explain that. But they represent the same object. The reason we do that is similar to when you do the phasor. We just try to simplify our calculation. When you transform the rectangular into a polar, when you do a multiplication or division, that's much easier as opposed to using that in a rectangular domain. So that's why we do a transformation. Now, once you do the Laplace transform, some of the benefit is going to show you is when you do a Laplace transformation, which we will show you later, when you get into the S domain, your differential equation will become an algebraic equation. Well, algebraic equations are easier to handle, right? So you solve in the algebra. You might not just only have one equation. You might have several algebra equation you solve for the unknown. And as long as you have enough number of the equation, you can solve for the unknown by using the algebra. So the ODE will become an algebra problem. You don't even need to do an integration or differentiation. So that will be much easier to deal with. That equation will be similar like this kind of equation. I hope that you still remember how you do a Laplace transform. when you change it into an S domain, then everything written as an S, there's no time in this equation. So everything, when you have time, you're going to convert into an S. Then once you write this one here, and when we solve it, we can simplify this by using a partial fraction expansion. If you do that, then the equation will be more like this. We're not giving you everything that you need to know how to solve this, but I give you like a general idea. Later on, we're going to fill the gap. We're going to show you how you can actually do this. Okay, now you might wonder, how can I get this equation? Well, if you look at the previous equation, I have a s squared minus 1 multiplied with a v sub s equal to something on the right. I simply divide that equation by s squared minus 1. And that equation is something that you're going to see when you actually apply the Laplace transform to your circuit. It will be some equation like this. You're going to be like a ratio of the two function of the s function, and you're going to simplify that by using a partial fraction expansion. The reason that we do this was because once you find this simple form, then you can apply the table, the 12.2 table, to give you the inverse Laplace transform. So we do a Laplace transform, we get the algebra equation. When you convert them back, you do what we call the inverse Laplace transform. And that will give you a time domain. That will give you the result in the time domain, which is a v sub t. And that is the goal that we try to solve. So you have two options. You can go through the time domain method, that you simply go through this, which is spend at least a half hour to solve this problem. If you do Laplace transform and you know how to use Laplace transform, that might just spend like 15 minutes to solve it. But you have to go through a transformation, you look at the table, and you can find a solution in this way. Both methods should give you the same result. That's the first advantage. The second advantage of this Laplace transform is this. The Laplace transform, unlike it's not only applied to the sinusoidal function, and it can be applied to the step and the impulse. Now, this is a very good advantage, because where do we see the step response? Where do we see the step function? We talk about step function. The step function is a simulation of a switch. And in the circuit, we got a lot of switch. So the step function is a step, is actually u sub t. If you have a u sub t, unless the function is sinusoidal, otherwise you cannot use phasor. If it's a rectangular equation, then like rectangular impulse, the pulse trend, you cannot simply use the phasor to solve it. And there's another function, it's called the impulse function. Impulse function, we use delta. The delta t is the impulse function. I'm not sure you guys know about the delta function, how the impulse function is working. But impulse function is very important. If you are double E, you're definitely going to see impulse function being used a lot. Impulse function is also called a function of the sampling function. So if you have a signal and then you can use the delta function to represent, I'm going to sample the signal at this particular time, you multiply with the impulse function, which will give you the value at that time. It's important when you do a sample. But a lot of different functions can be simplified by using this kind of functions. So it's not possible that you do a phasor. You can only do it in you can do it in the Laplace transform, but you cannot do it in the phasor domain. So the third thing we talk about is that you can give the complete solution. You will get it'll give you a complete solution. The complete solution includes the steady state response, plus the transient response. Okay, the transient response normally will die away when we talk about the phasor domain. We talk about that three different kind of a solution form. All of them has an exponential, and there's an exponential negative some power. And because it's the negative, is when time go to infinity, all these things will die away. It's going to be go to the zero. So we only care about the steady state response if you're dealing with the phasor. But the Laplace transform is even better. It can work for any kind of function that you have, and you will give you the complete solution with one of just one package, and then you can get a complete solution. Another thing I want to just talk about is the S over here. So let me take a look. Let's take a look at what the S is. So what is S? This S is actually a complex number. The S itself is a complex number. And if you look at we can represent S as some real number with an imaginary number, where the imaginary number is the omega. Now, what is the unit for the S? If you look at the equation that we have for the Laplace transform, it has an E minus S of t. And for E itself, exponential, this function doesn't have a unit, meaning the S times t should be unitless. If this one is unitless, then what is the unit for the S? The unit is 1/2. And what is the 1/2 tells us? 1/2 is hertz. It's hertz, so this is actually the S domain is actually what we call the frequency domain. Another frequency domain, which is Laplace transform, it's also give you a frequency domain. Just give you a general idea of what the Laplace transform is, which we are not going to cover in this course. So for the Laplace transform, for the Fourier transform, sorry, not Laplace.
What's the symbol where it says complex number equals plus J omega?
This is sigma.
Oh, okay.
Yeah, sigma. Okay, this is part of your textbook, which we don't have time to go over that. It's in the chapters 16 and 17. If you are interested, or in the future that you might want to take a look, it's a very important transformation. And a lot of things is actually based on the Fourier transform. You can also have an optical system doing a Fourier transformation as well. It's a very amazing discovery. So unfortunately, we don't have time. But if you look at this one here, the Fourier transform, you look at the Laplace transform. Laplace transform is this. They're very similar, right? The only difference is you replace the S with the J omega. With the J omega, the omega is also a frequency. So both of the S, one is the S is using the whole complex number, then the Fourier transform only use the imaginary part of this. That just want to give you a basic idea of what these two are representing. And in the future, when you hear about the frequency domain, you're going to hear frequency domain a lot, is they will represent the time information into a frequency information. It's most important for the periodic function, because the periodic function happen every couple of the period. How frequent that it repeats itself is what we call the frequency. If this is a periodic function, then it will be interesting to know how this repetitive will affect the function. So that's why we do a frequency domain. Even if you don't really understand this part, which is not easy, because this is really if you learn like a Fourier transform, and that would be take you like one semester to study that. But we wanted to just use the power of this Laplace transform, and we're going to show you how you can use that. So the two tables I'm telling you is these two, like 12.1 and 12.2. The 12.1 give you the Laplace transform, 12.2 give you like operational. The 12.1 is the functional. This is a functional Laplace transform, meaning if you have a function, like a very common function that we see in our circuit, and what is the result of the Laplace transform? Now, we didn't do the integration, right? But you can do the integration by itself to find out what is the Laplace transform for each one of the function. So that means if you have a function of f of t, you do, when we write this symbol represent, we're doing a Laplace transform. If I do a Laplace transform on this one, and the result in the f of s is going to be on the right-hand side. The right-hand column represents the Laplace transform. The left-hand side, the function in time domain. So one is in time domain, one is in the S domain, transform domain. We can do a very quick situation like how you do the integration. So if I wanted to get this one here, this is a step function. This is actually a unit step function. The magnitude of this one is 1. So if you draw a picture of this, this is what the unit function looks like. This is the function. This is the time. And this is going to be equal to 1. And your function is going to be like this. This is what we call the unit step function. U sub t is like this. If you do a Laplace transform, and the f of s is equal to the integration from 0 to infinity, and you use the function is use of t and dt. Oh, and you multiply the e minus st. Okay, so between time equal to 0 to infinity, what is the value of the u sub t? You look at the graph, the unit is equal to 1. It's just a constant. So I don't really need to have the u sub t for this equation. And what I ends up is I integrate e minus st from 0 to infinity, and integration of the exponential function is really a good thing to know. It's simply just the minus 1 over s, right? Is the coefficient of the t, take inverse of that, and that is the integration of that. But you also have to include the exponential function as well, and then you integrate from 0 to infinity. And then you replace the t from 0 to infinity. This is represent the t. Okay, so when time equal to infinity, and you got, let's make the 1 over s outside of this equation, e minus infinity minus e of 0. What is the time? What is the e minus infinity? That's equal to 0. And the e to the 0 is equal to 1. So then you have 1 over s minus 1. That is 1 over s. Okay. Again, in our class, we are not like a math class. We're not going to ask you to derive each one of them, but it's good that you know how to derive those things. Okay. But this is only for like a function, like a non-function, that if those functions are like these, well, for most of them, you probably have good enough to deal with the circuit. But maybe there's some other function that's not like this. Then you have to do something else to find a solution. And normally it's going to be a combination of these functions. And sometimes you might need something else to do to find a solution. And that something is what we call the operational transformation. The operational transformation is when you have a function of f of t, if you say you scale it up, you multiply that function with a time like a constant, you make it larger or make it smaller. That's what we call the multiplication. You have a combination of several different functions in time, and we want to do the Laplace transform at the same time. That will be the addition and subtraction. And most of the time, what you're going to see is we are going to have a differentiation of our time domain, because this is similarly like the V prime or the I prime, right? Our differentiation have this kind of form. How can I do a Laplace transform for this kind of equation? Well, it turns out to be like a very simple form in this way. Second derivative is also very common for our ODE equation, and that is going to be equal to the right-hand side. If you have more, and then, which is not going to happen in the circuit, so we only have like first order, second order, and then you can find a pattern. So the pattern is going to give you on the right-hand side. So this is one of the things you're going to do when we talk about chapter 13. We're going to change our equation into a Laplace transform equation, and this is what the operational transformation is going to be used for. Okay. I want to point out here why this is so good. Why this Laplace transform is so useful. If you look at the right-hand side, you can see when we have a first order derivative, you do a Laplace transform, you get this equation. The S is simply the S domain variable. Fs is the Fourier transform of the f of t. The F0 minus, what is that? This one here is our initial condition. This is also our initial condition, but this is the first derivative of our initial condition. This is a very like a V sub C. This will be like a dVc dt. So when we do a Laplace transform, you no longer need to do like once you find a complete solution, you take derivative, then you plug in the t equal to 0, and then you use this initial condition to find a coefficient. No, you don't need to do that. And then all these will be integrated into the Laplace transform. You simply put those values into here. But this also imply that you also need to find how to get those initial values. You have to find the initial value for the circuit first, such that you can put those values into this equation. Okay, another common things that we will use for the operational is the shifting. The shifting or the translation, these two are the things that we use a lot. Okay, these two represent the translation in time or the translation in frequency. The translation in time, meaning you have a function, but the function doesn't start from time equal to 0. It starts either earlier or later than time equal to 0. Then you have to do a shifting. When you do a shifting, the Laplace transform is going to multiply with an exponential function over here. If you shift in the Laplace transform domain, the S domain, this one is the shift, right? It doesn't start from the S, it starts from S plus some number. Then you're going to have the time domain to be shifted. On these two, you're going to see this a lot. When we do a transformation, you are going to use this kind of what we call the translation or shifting. One is the time shifting, one is the frequency shifting, and that is going to help you to get the correct equation. Okay, any question about this part? This is a very quick review. I don't know how good that your Laplace transform right now. If we give you a problem in the Laplace transform, how can you find the Laplace transform? Would you be able to solve the Laplace transform in maybe 20 minutes? So let me just give you one example over here, then I will end this lecture today. As I said, I'm going to give you some example in another video, which I will send out the link later. So the example is this. You might have a circuit that you give a power in this way. And with the power, I represented in terms of a figure, like a plot. And this is a voltage. So I'm given a voltage, and I give a voltage at certain time. So let me make a mark over here. This represents time equal to 1 second, 2, 3, and 4, etc., etc. The voltage has some amplitude. Let's say this is the phi on the top. I'm given the voltage, and this voltage is starting from time 0, but I didn't turn it on, so it was starting from 0. And suddenly when time equal to 1, I switch it on, so I turn on the switch, it goes to 5. So that means it's going to be 5 volts. And it will last for 2 seconds. After 2 seconds, I switch it off. Then it'll go back to 0 again. Okay. Now, if this is things that happen in your circuit, I wanted to solve my circuit, I want to see the behavior of my circuit, then how do you represent this one in time, and how do you solve this ODE? It will be a little bit challenging. But we can also use Laplace transform, and if you use Laplace transform, that is very easy. But if you want to use Laplace transform, you have a table where the table is this. This is the table. This is a table give you Laplace transform. Which equation can you use? Which formula can you use to represent that function that I just draw? Well, it turns out you need some practice to know how to represent that drawing that I just showed you and make it equal to this kind of combination of the simple equation that you see from this table. So let me show you how we can use a simple function to represent this. I can represent this one in terms of two different graphs. The one graph is this. This graph start from 1 and it will have a value of 5 and go over to the end. What is this called? This is a unit step function. This is not a unit step function, but this is a 5 times the unit step function, because step function is when you turn it on, it's going to go to the infinity and the value will not change. But this one doesn't start from 0. It starts from 1. And how do you represent that? It's not starting from 0. Well, if the use of 0 is equal to 1, that's the unit step function represent. How can I make this one to be at the time equal to 1, that will be equal to 0? Well, you write time minus 1, that will represent the unit step function of this graph. Meaning when time equal to 1, it will have a value that is use of 0 and is equal to 1. Less than use of 0, it will be equal to 0. Okay, so I got one of the function like this. Now, if you look at this function and compare it to the left, it's not equal, right? The one on the left is like a hump, and the hump only happen between the 1 and 3. But on the right-hand side, it go to the infinity. How can I make it going from 1 to 3? Well, I can make another function over here. And this function, 1, 2, 3, 4, this function starts at 3. And when it starts at 3, it goes to 5. And how do I represent this one here? If you know the previous one, this one will be u t minus 3. If I make the subtraction of these two, and that is actually the figure on the left, right? So how can I represent this v sub t? I can represent the v sub t in terms of the right-hand side, these two figures, meaning I can represent this function in the way of this. This is the equation to represent a function of v sub t, like a switch turned on at the 1 second and it only lasts for 2 seconds and you turn it off. This is a function to represent that. If this is a function provided to your circuit and you're going to use the Laplace transform method to solve it, the first thing you do is actually transform this, because this is a source. Later on, we're going to tell you what about the resistor, what about the inductor, what about the capacitor. Well, we can also do the Laplace transform to each one of them, just like we are making them into impedance. The impedance is going to be the S impedance. So, but how do we transform this? Well, then you look at the table that we have. What is the table they can give us a unit step function? This is a table that we know step function, if you have a use of t, is 1 over s. So let me write down over here. But you cannot simply use this one in our equation over here, because it's not simply just a use of t, it's a use of t minus 1. It's different. Why this is different? If you look at the second table, which is this one over here, you have a translation in time. The translation in time is in this format. Meaning my time domain is translated, it's moved to certain time, and the time is A is equal to 1, right? So how do I use this? When you use the translation in time, the first thing you do, you look at the right-hand side, what is the format of this? If you do a Laplace transform, let's say I do a Laplace transform of this. And I'm going to do the Laplace transform on this one here. So what is the ft minus a? Ft minus a is 5 as a constant. It never changes. Doesn't matter what a is. It's going to be 5. And you have a u sub t minus a, and as u a t minus 1, meaning a is equal to 1. And your f of t is equal to 5. Okay? Now, how do I take the Laplace transform of a constant? Then you go back. What is the Laplace transform of a constant? The Laplace transform of a constant is this. And what is the multiplication with a constant? Is this one here. Meaning if you have a 5 times the u sub t, and a k is going to carry to the Fourier transform, it's carried to the Laplace transform, it will be 5 times f of s. So that means Laplace transform is equal to 1 over s. That is simply the Laplace transform of u sub t. And because we multiply with 5, so it's going to be 5 over s. This is the Laplace transform of 5 u sub t. But how do you deal with the ut minus 1? Well, then you look at the translation. When you have a translation, you multiply e minus s, e minus as. So if you have a 5 ut minus 1, you do Laplace transform, you multiply e minus a. What is a? A is equal to 1. So e minus s, multiply with the f of s. With the f of s is actually 5 f of s, because there's a constant that is a 5 over s. So the Laplace transform of this is equal to this. Okay, similarly, if you look at the right-hand side of this function here, if you do a Laplace transform, what will it look like? It will be e minus as, where a is equal to 3. and you multiply with the Laplace transform of a phi ut. Phi ut is phi over s. Okay, and that means your Laplace transform, if you do Laplace transform of this voltage, your result is this is 3. And we represent this once a v sub s, which in the s domain, where you do a Laplace transform of this graph. And this is the Laplace transform of that. Okay. Any question about this part? All right. When you actually do the Laplace transform for the circuit, and we can just give you a quick idea what that is. Let's write down the equation for a circuit like this. If I take a Laplace transform of the left-hand side, and we also know v sub 0 is equal to k1, we also have another initial condition that is equal to k2. Then we take the Laplace transform, and you will see, how do you take the Laplace transform for second derivative? Well, you look at the operational here. This is operational. Derivative is here. The second derivative is the second one here. Then you can see there's a s squared fs minus sf f of 0. That is the first initial condition, and then the second initial condition. So if I do that, and let me write it down. Okay. So the first one is going to give you s squared, which is this one here. The f of s is the v sub s. Minus s of first initial condition, and minus the second initial condition. That represents this first term over here. And the second term is this one here. So if you write the Laplace transform of the second term, that is going to be 2 alpha times the first derivative. The first derivative, if you look at the operational table, is going to be s v sub s minus v sub 0. Okay, this is the first derivative. S times v sub s minus the first initial condition, that is the v0. And that is the equation of that. And then the third one, this is the blue one here, is this one here. Now the third one is this one here. What is that? Well, that one is going to give you omega 0 v sub s. And the right-hand side is the non-homogeneous part. The right-hand side here, that you're going to write it equal to f of s. Depends on what kind of function of t that is. If your function of time is this one here, which means I'm given my circuit, my second order RLC circuit with this input. What is the response? Then you have to convert the Laplace transform from the time domain, and sometimes they don't give you the equation, they give you a figure, and then you have to know how to convert the figure into a Laplace transform. And this is the Laplace transform of that function of time. And that's the equation that you put on the right-hand side. The f of s is simply just u of v of s. Once you do that, then all equation will become an algebraic equation. And the next time, when we come back from the exam, we will start to actually look at how we apply this to the circuit and how we're going to solve this. The most important part of this is that solving the equation is to simplify the equation into an expansion, the fraction expansion in simple form, such that you can do an inverse Laplace transform. Because the overall goal is to find the v sub t. And if you come back to what I was starting with, your goal is to make the v sub t equal to the series of s function, the s fraction. If I can simplify those into this kind of simple term, and you will see on the table 12.2, you can convert these back into the, not a 12.2, there's another inverse Laplace transform table. You can actually convert them back into a simple equation. And you can find out this time function from this. Okay, any question about today's lecture, Laplace transform? Okay, I want to encourage you put emphasis on this kind of problem. So in your homework, there's a couple of questions asking about this. It's simply just test your understanding, how to use the table 12.1, 12.2, how to convert a time signal into a Laplace transform domain, because that's the first step that you have to know how to solve a Laplace transform problem. Okay, question about this? Oh, if not, then we're gonna stop at here. As I said, I'm going to send out a video. The video is going to show you some of these things. I actually already solved the first one. That you should know how to use the first one. The second one is very similar, that you do a Laplace transform of e minus at. You can try it by yourself. Just see how do you do a Laplace transform of this function. Using the definition of the Laplace transform from 0 to infinity and put a function, always multiply with another function. This function is what we call the kernel function. The Laplace transform, Fourier transform have a different kernel function. Fourier transform is e minus j omega t. And you can find the solution of that. The next example is to show you how to do a Laplace transform for simple functions using the table. And the last one is similar one that I just show you. How do you find the Laplace transform for this different kind of graph? Using the idea how you combine function into a unit step function. It's probably is not just one simple equation, and there's going to be multiple of them. Okay, I'm going to end that here. And again, I'm going to send out the video link later. And in the meantime, your homework is due just right before the exam. On Wednesday, we're going to go over the simple exam on Canvas. So if you have time, go through those problems. I'm not sure we have enough time to go over all of them, but we will try to give you an idea how the exam looks like. Question about this? All right, I'll see you guys next time on Wednesday. Sorry about the messed up of the number. I will make sure that we're going to use the same number that you're you're in right now. I messed up with the number, sorry. So it's the 719-318-192. So, or you just click on the link on the course website. That will be the best way to get into the meeting. Okay, bye-bye.